Alright, so welcome to today's lesson. Today we're going to be talking about linear functions, and we've already spoken extensively on functions and what functions are. So just recall that functions are a relation in which each domain has exactly one range, each input has exactly one output, which means your x's don't repeat. So a function is a relation where your x's don't repeat. Today we're going to be focusing on functions that form lines, linear functions, and we've already spoken about that a bit in class. We're just going to dive even further into it. So let's start by defining a linear function. So we've spoken about this in class, and I've given you this definition in class before. So I haven't asked you to write it down, but we've talked about it. A linear function is just a function whose graph forms a line. The key term, though, is non-vertical, and I hope that makes sense, and we've spoken about this before. Why wouldn't a vertical line be a linear function? Well, because a vertical line isn't even a function. If you remember when we were trying to figure out which graphs were functions, we did the vertical line tests, and obviously the vertical line tests, or this vertical line would fail the vertical line test, so that wouldn't even be a function, let alone a linear function. So a linear function is just any function that forms a non-vertical line, like this, like this. It could even be a discrete linear function so long as it forms a non-vertical line. Okay, and we're going to be talking about that today extensively. So and another key thing here is that it has a constant rate of change, which means there's a constant the change in x corresponds to the change in y, and it's constant. And you'll see what I mean by that in a moment when we get to our next example, or not our next example, our first example. Alright, so here we have a problem, and we're going to really identify whether this is in fact a linear function. So a race car can travel 210 miles per hour. So miles per hour, per meaning that we're multiplying 210 by the amount of hours, per being one of your rate words. So they give you that equation, y equals 210x, where x would be your domain, and in this case would be the amount of hours. Okay, and the total distance traveled would depend on the amount of hours. That's why y would be your range value. And we're given a set of solutions as well, and the solutions are on this graph. So first of all, is this a function? Absolutely. If you look at your x values, do any of your x values repeat? No. Okay. And also, because this is a graph, you could have done the vertical line test as well, and that would also show that this is a function. Is this a linear function? It looks like it is. Just to make sure, though, remember with linear functions, you have to have a constant rate of change. So what I would do is I just put it in a table here. So we have 1, 2, 3, 4, and 5. Those are my domain values. Those are my x values, and y would be 210. 420, 630, 840, and 1050. So with our domain here, with our x values, what are we doing between consecutive terms? We're always adding 1. We're adding 1 every single time. That's constant rate of change in our x. Do we have a constant rate of change in our y values? Well, let's see. What are we doing between consecutive y terms? We are constantly adding 210. So first of all, just a little review from chapter 4. Would this be an arithmetic sequence? Absolutely, because we have that common difference. And would this be a linear function? Absolutely. We have a constant rate of change between with our x values and our y values. It's constant. So this would in fact be a linear function. So a constant change in x would in fact correspond with a constant change in y. So this is definitely a linear function. Okay, and normally when you're given equations like this, where both your x and y have powers of just one, it would be a linear function. Whereas, and we'll look at this in a moment, when we have exponents, they tend to not be linear, and we'll look at that in just a moment. So here we have y equals x squared, and we've spoken about the graph of y equals x squared a little bit already, and we're really going to focus on this in a couple of weeks. But first of all, let's see whether this is in fact a linear function. So we don't need to graph it to identify whether it forms a line. We could just take a look at it right away. Anytime you have an exponent of 2, you could right off the bat say, no, it's not going to be a linear function. No. Anytime you have an exponent of 2, or anytime you have an exponent other than 1, it won't be a linear function. Okay? So right away I know this is not going to be a linear function, but we could also just go ahead and test this out and see if we have a constant rate of change. Now we have a constant rate of change in our x values, right? But it has to correspond with a constant rate of change in our y values. And does that happen? No, it doesn't. Okay, if we look at this, we are adding 3, then we are adding 5, then we are adding 7, then we are adding 9. So it's not a constant change in your y's, so this would not be linear. Would it be a function? Well, do any of your x's repeat? No. And in fact, the graph of this would form, and we've taken a look at this in class a little bit, would form that U-shaped graph that we call a parabola. That looks like that. That would be the graph of y equals x squared. And if you do the vertical line test on this, you would see that it is a function. And we've done a ton of these when we were trying to find domain and range. So the domain would obviously be all reals, and the range would be y is greater than or equal to 0, just looking at the graph. But this would be a function. Would it be a linear function? Well, no, and you could tell by the table there, but you could also tell by just looking at the graph that is not a straight line. So another way that we could tell whether or not a function is a linear function is if it could be written in standard form. So any linear function can be written in standard form. If it can't be written in standard form, it's not a linear function. Now I want you to notice here, this is standard form, and I want you to highlight it or circle it. Well, first write it, and then once you write it down, circle it. This is important. This is standard function. So whenever you see an equation in the form of ax plus b y equals c, where a, b, and c are just numbers, are just real numbers, any real number, then it is a linear equation, and it would be a linear equation that's in standard form. Now notice the x's and the y's are all first power, the raised to the first power. If you ever see an exponent, right away you could say that is not a linear function. Okay, ax plus by equals c. So remember, a, b, and c are just real numbers, are just numbers. So a linear function could look like this: 3x plus 7y equals -8. So if you look at this, is this in the form of ax plus by equals c? Yes. A is 3, b is 7, c is -8. This would be a linear function, because any linear function can be written in standard form. This is standard form. This would be a linear function. Same with this. This would also be a linear function, where a would be 7, b would be -2, and c would be 7. So that would also be a linear function in standard form. All right, so let's take a look at this equation. Well, first of all, is this linear? If so, we need to graph it. Well, remember, in order for our function to be linear, you have to be able to write it in standard form, which is ax plus by equals c, and this happens to be in standard form, so definitely linear. No exponents on our two variables. Okay, now we need to graph it. So mostly we've been graphing just using tables of values. All right. We've touched on graphing with slope-intercept form. We're not going to do that. We're just going to do tables of values here. Now, if you look at this, we aren't given a specific set of domains that they want us to use. This also isn't a word problem, so we don't need to really focus on whether our domain is reasonable or not, which is what we did last week. We're just graphing this and we're forming a line, so we know that this is going to be continuous. We're going to have that line, and because we're going to have that straight non-vertical line, we know that our domain is going to be all reals, right? And we know that before we even graph it, okay? Because the domain of any linear function is going to be all reals. So when we are graphing this, we could just choose any domain value that we wish. But the first thing we need to do is to make it easier to make our table of values is solve this for y. And this goes back to what we did a few weeks ago with literal equations. So we're going to want to move everything out of the way so that y is by itself. Well, that's pretty simple. The only thing we need to get rid of is 2x. So we would just subtract by 2x on both sides. And we would be left with y equals 4 minus 2x, or negative 2x plus 4. That's going to make it a lot easier for us to make our table. So with linear functions, you're going to want to get 3 or 4 points on there to get a good line. So again, our domain is all real, so it doesn't matter which 3 points you choose. I'll just go ahead and choose negative 1, 0, and 2. So if we plug negative 1 in here, that's negative 2 times negative 1 plus 4, which would be 6. So first ordered pair would be negative 1 comma 6. If we plug in 0, it's negative 2 times 0 plus 4, so our y would be 4. So our second ordered pair would be 0 comma 4. And if we plug in 2, it would be negative 2 times 2 plus 4, which would be 0. So our last ordered pair would be 2 comma 0. And if you plot this, your first ordered pair is negative 1, 6, which would be right here. Okay. Your second ordered pair would be 0, 4, which would be right here. And your third ordered pair would be 2, 0, which would be, whoops, that's not 2. I'm sorry, I actually messed up on this point. This is not negative 1, 6, because negative 1 would be between 0 and 1, so negative 1, 6 would actually be right here. Okay, so that would be your 3 points. Those would be your 3 points. And it's continuous, so we are going to go ahead and connect them with a line. And you could obviously see that it is linear. Right here, x plus y squared equals 4, so standard form is ax plus by equals c. We don't even have to worry about that because we have y squared. We have an exponent, so this is not a linear function. This is not a linear function, so we would not have to graph it. Anytime you see an exponent on one of your variables, it's not going to be a linear function. So just a recap of what a discrete function is and a continuous function. So we already know what they are. Just remember, discrete means we have unconnected points. We have unconnected points, whereas continuous, we're going to have a function whose graph is either a line or a curve. And because we're talking specifically about linear functions today, it's going to be a continuous linear function is going to be a function whose graph is an unbroken line. Whereas a discrete linear function is a function that has unconnected points that form a line. So it would still be linear. So let's take a look at some examples of this by doing some word problems. Alright, so Sal opens a new video store and pays the film studios $2 for each DVD he buys from them. So that can be shown given this function f of x equals 2x, where x is the number of DVDs purchased. So in our previous example, we weren't given x is the number of DVDs purchased. We weren't given a domain, a specific set of domains that they wanted us to use. So I said, well, then therefore our domain is all reals. But remember, The reason why I said that is because we weren't dealing with a real-world situation. When we're dealing with real-world situations, we need to consider whether the domain is actually reasonable in this real-world situation. So in this case, our domain is not going to be all reals. And I want you to think about that for a moment and think about why it's not all reals. And just take a moment to pause and think about why it's not all reals while I write this stuff down. So if we think about this, remember, X stands for the number of DVDs purchased. So is it reasonable for Sal to purchase a negative amount of DVDs? No, it isn't. So obviously we're not going to have any negative X's. We're not going to have any negative inputs. So we're going to start at 0. Because there is a chance that he might not buy any DVDs at all. So it could be 0. Now, would it make sense that he might buy 5/10 of a DVD or 1/2 of a DVD? No. He's not going to buy portions of a DVD. He's just going to buy whole DVDs. We're going to be dealing with whole numbers here. So 0.5 isn't a reasonable domain, but 1 is, 2 is, 3 is, and so forth and so forth. And he could buy a very huge amount of DVDs if he wanted to, but it's going to be whole numbers. Okay? We're not dealing with any parts. We're not dealing with any fractions. So let's go ahead and graph this and see if this is in fact a linear function. So if we graph this, we're going to first want to do a table here. So if we do our table, and this is pretty simple, it's just 2 times x, so it's pretty simple to find our y values, our range. So if we have 0, the y would be 2 times 0, which is just 0. So if we have 1, your y would just be 2 times 1, which would be 2, right? If we have 2, your y would just be 2 times 2, which would be 4, right? And if we have 3, your y would just be 2 times 3, which would be 6. So obviously this is linear. I mean, if you look at your x's are going up by 1 every time. Your y's are going up by 2 every time. And I'll go ahead and write that down for you. So there's a constant rate of change between both the x and the y values. So this is obviously linear, but let's go ahead and I didn't put this in your notes, I'm sorry. You're going to actually have to draw a little coordinate plane, or at least quadrant 1 of a coordinate plane, and this would be 0, 1, 2, 3, and we'll just stop there, and then this would be 1, 2, 3, okay, and this would be number of DVDs, right? Whereas this would be cost. So at 0, his cost is obviously going to be 0. Let me do this with another color. And that's our first ordered pair, 0, 0. At 1, his cost is going to be $2. At 2, his cost is going to be $4, which, let me add a 4 here. 2, his cost is going to be $4, and so forth and so forth. So now, are we going to connect this with a line? Well, when you connect this with a line, what are you really doing? You're saying that this is continuous, and that the answer could be any of the terms that are part of this line, which would include your decimals and your parts and your fractions. And we know that that wouldn't be reasonable. So we can't have parts of DVDs being sold. So we're just going to have to leave it like this. So what kind of a linear function is this? This is a linear function. This is a discrete linear function. It's a discrete linear function because it's just made up of points. Discrete linear function, and the domain is going to be, well, it's just 0, 1, 2, 3, and so on and so on and so on. Whereas your range is going to be, well, our range values, I erased it, but it was 0, 2, 4, 6, and so forth and so forth and so forth. And that would be it. I'll go ahead and let you read this on your own because we're running this video is kind of long already. But it says she pays $1 to her grandfather for each hour of operation, right? So that's given to us by this very easy function, which is f of x equals x, where x is the number of hours her booth is open. Okay, so let's talk about reasonableness. Is any value of x reasonable for this problem? No, it wouldn't make sense for her to work a negative amount of hours, right? So we'll have to start at 0. It's not going to make sense for us to have any negative numbers. But let's talk about our domain a bit more, though. Can we have parts? Can we have fractions? Can we have a fraction of an hour? Absolutely. She could work part of an hour. She could work a fraction of an hour. In fact, if you think of it, time is in fact continuous, right? Time doesn't have just a bunch of patches where we jump from one whole number to another. Time is continuous. So this is going to be continuous to a point. It's going to be continuous after any x value that is greater than or equal to 0 because time is continuous, and we could break time up into fractions and parts. Okay, so in this case, it is going to be a continuous function, continuous linear function after x is greater than or equal to 0. Let's go ahead and graph it now with a table, and this is going to be a very simple table because it's just f of x equals x, right? So if x is 0, y would be y would be 0. I'm sorry. If x is 1, y would be 1. If x is 2, y would be 2, and so forth and so forth and so forth. So how would we plot this? Well, our first ordered pair is 0, 0, which is right here. Our second ordered pair is 1, 1, which is right here. Our third ordered pair is 2, 2, which is right here. And it would be continuous for any value after x is after 0. It's going to be x for any value greater than or equal to 0. For any x value that's greater than or equal to 0. So we are going to have to draw a line to show that it's continuous for any value for any x value that is greater than or equal to 0. So what is the domain for this? Well, if you look at the graph here, and remember how we find domain, we scan from left to right. It's just any value, any x value that is greater than or equal to 0, right? And if we look at the range, well, what's the range for this? If we scan from bottom to top, the range is also going to be any value greater than or equal to 0. Y is going to be any value that's greater than or equal to 0. All right, that's it. All right, hope you have a great day. See you tomorrow.